How do you solve for the equilibrium constant? So first, what actually is the equilibrium constant? So in any reaction, if you have reactant A plus reactant B yielding reactant C plus reactant D, then the formula for the equilibrium constant will be your products to the power of however many moles there are of each product over the reactants to the power of however many moles of each reactant. Now the equilibrium constant deals with molarity, meaning that the numbers that we input into this equation must be in molarity. However, the equilibrium constant is not a measure of molarity, but it's just a ratio of products over reactants. So let's look at the problem. A closed system initially containing 1.00 times 10 to the negative 3 molar hydrogen and 2.00 times 10 to the negative 3 molar iodine at 448 Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of hydrogen iodide is 1.87 times 10 to the negative 3 molar. Calculate Kc at 448 Celsius for the reaction taking place, which is the following. So how do we approach this problem? The first thing we're going to do is set up something called an ice table. We essentially take our reaction and we include each reactant and the product. And we use an ice table to represent the initial, the change, and the equilibrium concentrations of each. One important thing to note is that we only include gases and aqueous solutions in our ice table and in our equilibrium constant. Let's start out by filling in what we know in this table. The first thing that you know about any ice table is that you have 0 of the products. This is because the reaction hasn't started yet, so we haven't produced anything. We know a couple other pieces of information, like the initial concentration of hydrogen and the initial concentration of iodine. We also know one other thing. We know the concentration of hydrogen iodide at equilibrium. Now with this information, we can now fill in the change row since we know the difference between the initial row and the equilibrium row for the product. And the change row is simply the difference. In this case, we go from 0 to 1.87 times 10 to the negative 3rd molarity. So that will be our change. Now, since we have 2 moles of hydrogen iodide for every mole of hydrogen and for every mole of iodine, this means that for every 1.87 times 10 to the negative 3rd molarity that we're adding to go from initial to equilibrium, we will lose half of that amount for each of these two, since we have 2 moles of HI and only 1 mole of H2 and 1 mole of I2. Now, the reason why this will be a negative value is because products are produced, meaning this will be positive, and reactants are consumed, meaning this will be negative. Again, it is important to note that we will lose half of the amount of reactants that we will gain of product, since again, the equation shows that we gain 2 moles of hydrogen iodide for every mole of hydrogen and every mole of iodine. We can now simply do the math and take the initial row minus the change row to find our equilibrium row. Now that we've solved for the values in our equilibrium row, we can plug these values into our equilibrium constant formula to find the equilibrium constant. And we get about 51, meaning that Kc, or our equilibrium constant, is 51. Let's take a look at another problem. A closed system initially containing 1 molar hydrogen and 2 molar iodine at 448 Celsius. The equilibrium constant equals 50.5. What are the equilibrium concentrations of H2, I2, and HI, given the following reaction? So, we're going to use an ice table for this problem. But instead of solving for the equilibrium constant, we need to solve for the equilibrium concentrations. So again, let's fill in what we know in this ice table. We know the initial concentrations of hydrogen and iodine, because they are provided, and we know the concentration of our product, hydrogen iodide, is going to be 0 before the reaction started, since it's the initial row. Now, unlike the last problem, we're not provided with any equilibrium concentrations, meaning that we don't know any of the changes. This means that we have to use X as a placeholder. Again, since we have 2 moles of hydrogen iodide, this will be plus 2x, while we only have 1 mole of hydrogen and 1 mole of iodine, meaning this will be minus x. We can now write out the equilibrium concentration in terms of x. Now, we have the equilibrium concentrations, but we need to solve for x to actually find the real numbers. Fortunately, we are provided with the equilibrium constant. So, we're going to plug these numbers into our formula and then solve for x. Now here we've plugged in the equilibrium concentration into our equilibrium constant formula, where we get 2x squared, since there are again 2 moles of hydrogen iodide, over 1.0 minus x times 2.0 minus x. which will equal our equilibrium constant of 50.5. Now, all we have to do is solve for x. We have multiplied both sides by 1.00 minus x and 2.00 minus x, which results in the following equation. We can then subtract 4x squared from both sides to get a quadratic equation. Now we can simply use the quadratic formula. Now we have found two possible values for x, but only one of them is correct. Now we cannot have negative equilibrium concentrations, so 2.323 is not possible for our x value, since that would make the concentration of hydrogen negative and the concentration of iodine negative. Therefore, x equals 0.935. Now let's plug in for x and find the final equilibrium concentration. We have now solved for the equilibrium concentration. Thanks for watching. Like and subscribe.